bycatch reduction device, testing Pacific halibut bycatch reduction techniques, and examining the efficacy of T90 mesh cod ends to improve catch composition. Mark has a master's degree in marine fisheries biology from Humboldt State University and a PhD degree in fishing gear technology from the University of Tromsø, the Arctic University of Norway. Questions during today's presentations can be submitted via the Questions tab on your control panel, and these will be read aloud by the moderator at the end of the presentation. Today's seminar will be recorded and should be available on our website later this week. All right, feel free to take it away, Mark.
Great, thanks, Claude. Can you hear me all right?
You bet.
Great. Yeah, well, hello, everybody. Good morning. Thank you for tuning in. My name is Mark Lomeli. I'm with the Pacific States Marine Fisheries Commission, and we'll be talking about gear modifications and trawl and longline fisheries to optimize species selectivity. I want to acknowledge all the other people that were participated in the work that will be presented in this talk. They're listed here in this cover slide. So thank you to everybody that's contributed to this. So just kind of starting out, just real general, looking at sort of tactics to reduce bycatch or alter selectivity. You have your geographic area fished, can be a method. Fleet communication, fishers communicate about hotspots or a lack of hotspots, could be a method. Time of day, research has shown that species behaviors can change between night and day. And then we have examples of temporal or spatial closures can also be a tactic. And then you have your gear modifications, and that's what this talk will be focusing on. And you can do that in a couple of different ways. You can have the morphology of an animal, and you can look at those sorting grids or alterations to meshes or hook modifications, or just some examples you can exploit the morphology of an animal. Then you can have the behavior and how an animal responds to gear components. It can be another one. So we're focusing today on just the gear modifications. So just a quick background of all this work. As you know, the directed commercial fishery for Pacific halibut ranges from Northern California to Bering Sea, and it is a longline based fishery. In mobile and fixed gears, bycatch of halibut can occur in considerable numbers at time, and retention of this fish is prohibited in these non-directed fisheries. So fishers are not allowed to retain the halibut, and often in these commercial fisheries, it's deducted from their quotas. So there's really no incentive for fishers to be targeting halibut. So they're just an incidental bycatch. But so yeah, they have to be released. And this source of mortality, directly impacts the available harvest of halibut to the directed fisheries, whether it's commercial or recreational. For trawl fisheries, they comprise the majority of Pacific halibut bycatch. Typically, they tend to encounter younger fish than the directed Pacific halibut fisheries, and generally have a higher discard mortality rates. And so, being able to develop and identify methods to reduce halibut mortality is important. This here is an image here of the United States West Coast, and this is kind of this oval-shaped red circle, or red oval, excuse me, that is kind of focusing where this talk is going, research has occurred. So it's ranging from the Oregon and Washington coast is where this presentation is focusing on for location. So this here is a selective flatfish trawl for the research we'll be presenting that pertains to trawl gear. This is the trawl that was used in all of those trials. This was developed in the early 2000s as a device to try to reduce rockfish bycatch in the groundfish bottom trawl fishery off the West Coast. During that time, there were several overfished and rebuilding rockfish stocks. And so this net was designed to allow fishers to target flatfishes while reducing catches of rockfish. It has a head rope that fishes about 1.3 meters above the seafloor, so it's a very low rise trawl. And further, it has the head rope that fishes back behind the foot rope, so that it has a cut back head rope. And the function of that is as fish come in contact with ground gear, fishes that may have a tendency to rise up higher in the water column as they interact with that gear, or species that are just off the bottom a little bit, they can have the opportunity to rise up over that head rope and not be retained in the trawl. This net has shown very effective at reducing canary rockfish bycatch, but no less effective as some of the other rockfishes. But that's the intent and design of this trawl, and this is what we used in our studies. And here's just a schematic diagram illustrating this selective flatfish trawl to sort of typical bottom trawl on the top. It is the head rope is fishing forward of the fishing line, so this would be like a hooded trawl, and then there on the bottom you see the head rope that's cut back on that selective flatfish trawl. So just to kind of give you an idea of the differences between these trawl designs. So I'll start off talking just a little bit about sorting grids, and we'll be using these to exploit the morphology of fish to alter our selectivity. So here's a sorting grid device that is designed to reduce Pacific halibut bycatch in the West Coast groundfish bottom trawl fishery. And this design specifically would be used by fishers seeking to target assemblages of flatfishes and roundfishes. How this design works, it has two vertical sorting grid panels that extend longitudinally down a section of netting. And it has squares, and in this specific design, the squares are 7-inch squares. And the concept to this design is that if a fish can pass through those grids, then they can move back towards the caught end and be retained. If a fish physically cannot pass through the grids, or just chooses not to go through the grids, then the fish is ultimately then released out the trawl via an exit ramp. And this, So on this design, it had this circular ring system put into it. It's a really novel design. It was developed in Sweden in collaboration with Dan Trawl. It's a net manufacturer in Seattle. And in this flume tank pictures on the top left and bottom left, what it illustrates is, it really gives a fixed shape of that bycatch reduction of ice area. So you see forward of that circular ring system where the net is sort of stretched and kind of collapsed a little bit, but where those rings are at, there's a nice circular shape. So you're trying to give the gear its best opportunity to perform. As most of the vessels, or all the vessels, have fishing net reels that got to wind the gear up onto it. This gear needs to be designed to be flexible. It can come onto a net reel. And so these rings are made up of interlocking nylon cylinders, and they're held together by shock cord. And so when they come up, they can collapse and be brought to the net reel, which is what you see in the bottom right image. And when they're deployed, they bounce back into a circular shape. And here's just an image of the Dan Trawl net lock of that circular ring system being installed onto the net. So for the methods or sea trials, we completed 30 tows. They were conducted shoreward of the rockfish conservation area off of northern Washington. This work was on the fishing vessel Miss Leona. To look at our escape net and gear performance, we used a recapture net to quantify our catches. So essentially, any fish that was excluded from the excluder out the exit ramp, we caught it in an auxiliary net. So we had a recapture bag over that escape area to collect those animals escaping. And then length data was collected to sort of examine the size selectivity of that gear on commercial Pacific halibut and other target species. So then looking at the results, here's the selectivity for Pacific halibut. On your y-axis would be the retention probability of being retained in the caught end of the trawl. It ranges from 0 to 1. The x-axis is your length. And these are the grade circles. Those are our experimental data or our observed catches. Dashed lines are 95% confidence intervals, and then the solid black line is our mean modeled value. And what we're looking for is commonly used as like an L50 value. And your L50 value is the length at which 50% of the fish are being retained. or you can look at it vice versa, the length was 50% are not being retained. But for this experiment, we see halibut about approximately 72 centimeters in length. There's a 50% probability of retaining those fish in the trawl caught end. We look now further down at the L25. This is where 25% of the fish are being retained. And this is lengths now approximately 79 centimeters in length. So for a Pacific halibut, 79 centimeters in length, 75% of those fish will be released from the trawl using this specific gear during our gear trials and the time that they were conducted. Overall, the bycatch reduction of halibut was 61% by weight and then 57% by numbers. So overall it did a very good job at excluding these sort of mid to larger sized Pacific halibut. Looking at our targets catch, here we have a range from 90 down to 77%. For lingcod, Pacific cod, the retention was around 90% retention. The lowest was arrowtooth flounder at 77%. We look at some of the other target flatfishes such as English sole, wreck sole, Dover sole. The retention of those fish are probably the mid to upper 80s. So overall, there's a relatively high retention rate, but there's obviously some catch loss associated with using this gear, and so it's something that fishers would need to consider when making gear alterations to reduce bycatch or alter selectivity. Is what are the trade-offs between bycatch reduction and target catch? And then we see real low retention rates for long nose skate and big skate, but that we expect. They're such large animals, and they're not going to pass through a square that's a size of 7.5 inch. Here's an example of one of the tows that we made. On the left-hand side, that is the caught end catch. There it's an 89% retention by weight for that particular tow. On the right-hand side, that's the Pacific halibut. We had a 61% reduction in their bycatch. And in the top is the target catch that was in the recapture bag. And here's just a short video clip illustrating the kind of the gear. This is the very front of the gear. As fish come in and encounter the grid systems, you'll see some of the fish passing through those grids, and then they'll begin to move back towards the caught end. Here's a camera in the caught end that's looking forward. That's the exit ramp in front of you. And these are all fish that have passed through those grids and moving back towards the caught end, or are en route to go into that recapture bag. Which kind of just gives you a little bit of a sense of how the gear is working. Now, this is papers in the Journal Fisheries Research. If I can see more about it or more details on exactly what we did, it can be located there. Or if you can contact myself or Waldo Wakefield, and we can get a copy of that to you. So here is another sorting grid device we looked at. And what this device here is, how it differs is that this is designed for fishers that would look to target just flat fishes. So it has a similar concept as the previous talk or study, where it has vertical sorting grids that extend longitudinally down a section of netting. But rather than having the squares, we've now changed the grids down to elongated slots to allow these flat fishes to kind of slide through. We've looked at 1 3/4 inch, 8.5 inch grids, 2 inch and 12 inch slots have also been tested. But for this particular data set I'll show you here, this is coming from elongated slots with 2 inch by 10 inch openings. So just a little background on this project. There's limited quotas available relative to the more abundant and productive flatfish stocks. So for example, in 2014, this is when this project was performed. The groundfish bottom trawl fisheries shoreside trawl and catch limit and bycatch quotas were these listed below. And so you see your target flatfishes for Dover sole, 22,000 metric tons, English sole, a little over 5,000, arrowtooth, a little over 3,000, and trolley sole, a little over 2,000. But then you look at sort of the species that are constraining the harvest of those flatfishes. And we have a sablefish, a little over 2,000 pounds. Sablefish are largely caught in conjunction with the Dover sole. So you can see there's a really large discrepancy in the available catch for the species. just a few hundred metric tons for dark blotch, and then canary and Pacific halibut bycatch is not very high. So that's sort of the reasoning for developing and testing this device. So this project, trials were conducted off Oregon. We worked with the fishing vessel Miss Sue, and this was in June of 2014. Our tow durations ranged anywhere from 45 minutes to 2 hours. We towed at common tow speeds for the fishery of 2.2 to 2.6 knots. And this fishery, just kind of put it in context, tows typically range from 2 to 6 hours in length. And there are, at those tow durations, tow speeds that we looked at, we were able to complete 38 tows at an average bottom depth of about 100 fathoms. As in the previous work, we used a recapture net to look at fish retention and escapement. So looking at the results of this work, here's our flatfish catches. The y-axis is retention probability. The x will be length. On top, we have English sole and rec sole. Across the length classes that we encountered, we see relatively high retention rates in the caught in for those flatfishes. They are a smaller size flatfishes, so they're easily can pass through those grids a little bit more. We look at our larger sized flatfishes such as arrowtooth flounder, Dover sole in the middle frames, and then the bottom left, petrale sole. And what we see is we start pushing towards 40 centimeters in length. We begin to see a drop off in the retention of those fish as they're starting to become just a little bit too big to pass through those grids. Looking at the bottom right hand side, Pacific halibut, we see a very low retention rate across the length classes that we encountered. So it did a very good job at reducing halibut bycatch. Here in this red, this is the percent retention overall by weight, all lengths combined. For English sole and rec sole, we see approximately 87% retention for both of those species. Arrowtooth flounder, about 85% retention overall, and Dover sole and petrale sole were close to 90% caught in retention. And then Pacific halibut, only 21% were retained. So you're looking at approximately a 78% reduction in your Pacific halibut bycatch with this device. So it performed really well at doing that. Looking at rockfishes, again, our retention probabilities, the Y with our lengths, and the X. We have a shelf rockfish complex. We pulled those species into that graph, and then we have the slope rockfish. And then below is a green striped rockfish that is a shelf rockfish species, and dark blotched, which is a slope rockfish. And really here, this gears really steep selectivity curve for these species. As it gets to around 30 centimeters of length, you really see in this area here, really steep drops offs in the selectivities of it. So it does a really good job at getting these, once they get a little bit larger, getting them out. The caught in retention overall for green striped rockfish, approximately 47%, and then dark blotched, you retained about 55% of those fish. Looking at roundfishes, sablefish and lingcod. Again, really steep selectivity curves here. For sablefish and lingcod, you start getting close to 40 centimeters of length. It's doing a really good job at not allowing those fish to pass through those grids, and it's reducing their catches. Overall, sablefish retention was approximately 26%, lingcod 4.5%, so it's getting out close to 95% of the lingcod reduction. So it really shows a big contrast between its ability to retain flatfishes but exclude roundfishes. And this is just a short video clip just kind of illustrating the gear and its selectivity. This is a caught in catch of Dover sole, petrale sole, and arrowtooth flounder. You see there lots of flatfishes, and we're just basketing them up, getting them ready to get weighed and length sampled. But yeah, lots of flatfishes in that main catch. And then here it'll transition into the recaptured bags catch. And here you're going to see lots of sablefish, skates, lingcod, and larger sized rockfish. So it just really shows just the dramatic difference in the catchability of introducing this types of grid to target flatfishes. And here you're looking at primarily petrale sole and some Dover sole mixed in. That's the caught in catch. And then here is the recaptured bags catch, consisting of a large catch of lingcod, but also mixed in there, there's canary rockfish and some Pacific halibut. Okay. And this work, it's in the Journal of Marine and Coastal Fisheries, so it can be located there to read more in depth about what went on with all that work, or contact one of the authors on that paper and we can provide a copy if you wish. Okay, so that kind of ends the sort of the sorting grids and exploiting fish's morphology to optimize selectivity. Now I want to kind of switch and focus a little bit on using fish's behavior to reduce their bycatch. And this would be the efficacy of illumination to reduce Pacific halibut bycatch in the United States West Coast groundfish bottom trawl. The background of this study, some research has suggested that halibut bycatch in the West Coast groundfish bottom trawl fishery could potentially be reduced using artificial illumination. So in a study that was investigating whether illuminating the head rope of that selective flatfish trawl could reduce rockfish bycatch, results show that the illuminated trawl on average caught 57% less Pacific halibut than the non-illuminated trawl. The result in that study, however, was not significant. It was likely due to a limited number of halibut caught. And the asterisk there, that's the paper, that the previous study that I'm referring to. So you can look in and track that down if you want to see more specifics about that background. And in that previous work, as I mentioned, they used a selective flatfish trawl. The head rope is approximately 130 feet in length, I believe. And along there, we placed illumination along the head rope and up along to the wing. So we really had the whole kind of head ropes and wing area illuminated, trying to see if we could reduce rockfish bycatch. These are the results from that previous work. This is a change in average catch efficiency graph. So basically, there's no difference between your two trawls, your illuminated and non-illuminated trawl. Your value is going to be 0. If it's above the value of 0, then your non-illuminated trawl is catching more. If it's below 0, then the illuminated trawl is catching more. And what it shows here for Pacific halibut, we see that 57% less catch in the illuminated trawl. However, when we incorporate our confidence intervals into that, it extends above the value of 0. We can't really detect any significance with that. It didn't work on rockfishes. We didn't see any difference between the two trawls in terms of their catch efficiency. We did see a catch reduction in Dover sole and sablefish in the non-illuminated trawl in that previous work. Also, in that same work, light levels were measured at the altitude of the head rope, and it showed that the ground gear components often created mud clouds that rose above that head rope. So I mentioned earlier that head rope is only fishing about 1.3 meters above the seafloor, and so if the duration of that mud cloud was considerable, it could affect fish's ability to detect and respond to the illumination that is along that head rope, and essentially just maybe not be effective. It's being drowned out. So what this really suggests is that there may be potential to reduce halibut bycatch using lights, but that perhaps the placement of the lights on the trawl gear itself could be in areas that are less impacted by the mud clouds. For example, maybe the wingtips or the upper bridles. They could be it could be a factor in their potential efficacy, and so that kind of resulted in this study of seeing if we move these lights in certain areas, can we get a reduction in catch? So the objective here is we want to determine whether illumination can reduce halibut bycatch, but also we want to look at its relationship with the physiological condition and or the stress levels of captured halibut. Here again is that selective flatfish trawl. This trawl just kind of show you to illustrate the upper bridles. So on the left-hand image, the numbers 1 through 3, that's the upper bridle. So the bridle is very short compared to other trawl designs. It's about 9 feet in length. But those are the placements of the lights along that upper bridle. We did that on the port and starboard side. But we also put a cluster of lights on the breast line and a couple at the very front of those wingtips. So we had 6 locations of lights set up. Here's just an image of the trawl being deployed. You can clearly see the LEDs on the bridles and wingtips going out. And then just another picture illustrating the lights attached onto the trawl being deployed. The methods this work, the trawl was fished with and without artificial lights on the upper bridles and wingtips in an alternating order. So we did this to create paired tows for the analysis. We used green LED fishing lights. Specifically, they're the Lindgren-Pittman Electrolume fishing lights. They're centered on 519 nanometers. And then we also wanted to measure the light levels at the trawl depths with and without artificial illumination on the trawl. And we did this using the Wildlife Computers TDR MK9 archival tags. And what these do is they provide a relative unit of light. And we then take this tag and calibrate it to a known given light level using a PAR sensor in a controlled laboratory setting. And then with that information, we can then create a function that will allow us to convert those relative light units to irradiance units. And so that's how we measured our light level. As I mentioned, one of the other objectives was getting physiological data on Pacific halibut between the two trawls. And so blood samples were collected via caudal puncture from 51 halibut to measure the stress indicators, glucose, lactate, and cortisol. Fish condition was estimated using Fulton's condition factor. We had a sample size of 204 halibut for that data set. And then using a distilled fish fat meter, we measured the somatic fat content for 201 halibut. Here, this red circles, that's the area of the caudal puncture where the blood samples were taken to look at those stress indicators, glucose, lactate, and cortisol. And then here on this image this is where our fat meter readings were collected. So we took two measurements for the blind side and for the eyed side. And what this is going to provide us is an indirect measurement of energy available to the fish. Here's an image that is Dana Rudy from the IPHC. She came out on a leg on the project with us, and she's just there taking a caudal puncture from that Pacific halibut. She'd then put that on a sample on ice and then take it into a laboratory setting inside the vessel's galley and centrifuge it, and then further prepare it for storage and subsequent analysis. And here is the fat meter being used on a Pacific halibut. That's Heather Rittman who's performing that. She was out during that project assisting, and she is from H&R Sustainability. So our findings on this one, here's a short, I'll give you a few minutes to look at this image, and we'll see if you guys can spot any Pacific halibut and how many you may be able to see in this image. I'll just give you a few seconds to do that. The mix of species you see here, lots of lingcod, petrale, sole, canary rockfish, sablefish, and skates. So there's a wide mix of groundfishes in here. All right, so what we've got here, we got one right there. We got another one over here. It's hanging out under the tail of a lingcod. And then we have a third one right in there. So hopefully you guys found all three. And then there's more in there. Those are just the surface, just the scratching. So looking at the selectivity for Pacific halibut, this left-hand graph, that's a catch comparison analysis. And what this shows is there's a baseline value of 0.5. That is that horizontal line that's right at the 0.5 value. If there's no difference in the catch comparison between the two trawls, then our value is going to be 0.5. If it's above that, the control trawl is catching more. If it's below that, your illuminated trawl is catching more. The circles are observed values. The dashed lines, again, are confidence intervals, and then the curved solid line is our mean fitted value. The gray lines, that's the number of fish. And what this tells us, our confidence intervals are below that point value. So we have a significant length-dependent catch effect for Pacific halibut. And here what it's showing is that the illuminated trawl is catching significantly fewer Pacific halibut across that length range, which is 62 to 126 centimeters in this particular case. So then to quantify the effect of that length-dependent catch, so then we use the catch ratio analysis. That is the graph that's on the right-hand side. And if the catch ratio is the same, the value would be 1. And what we see here is to quantify that length dependent effect is telling us that the illuminated trawl is only catching 36% of the number of Pacific halibut compared to that of what the unilluminated trawl is catching. So you have a very strong significant reduction in Pacific halibut bycatch using artificial illumination. Looking then at the target catch. Here we have Dover sole and petrale sole. The left-hand side is our Dover sole, that vertical dashed line, that's for Dover sole and the petrale sole graph. Those are the minimum market value for the fish plants. So just kind of gives you an idea of where's a marketable sized fish in these number of fish graphs. And what it shows us here for Dover sole, this red oval kind of shows you that's the bulk of our fish that's sampled. And we really don't see any significant length dependent effect between their confidence intervals or above and below that value of 0.5. So statistically, there's no significance. We see on the lower length classes and a few of the upper length classes in that graph, it does show that there's a significant length dependent effect, with the illuminated trawl catching significantly fewer. The number of fish sampled there and the sample size that are so low, but really the strength of that data is in that red circle. Looking at petrale sole, we see a significant length dependent effect for fish approximately 44 to 50 centimeters in length, with fewer fish of those lengths being caught in the illuminated trawl, excuse me. But for the other length classes, it's showing no significant effect in the catch between the two trawls. For sablefish and lingcod, here for sablefish, we see a slight length dependent effect in the catch, with the illuminated trawl catching significantly fewer sablefish, approximately 44 to 50 centimeters in length. Outside of that length classes, there's no difference. Looking at lingcod, we see no length dependent catch effect across any of the lengths classes that we sampled. So this here is the change in average catch efficiency graph. This just takes all the lengths and it pulls it into one analysis and just look at the catches overall and its effect. What we see here for Pacific halibut, the illuminated trawl caught 58% fewer halibut than the non-illuminated trawl. For sablefish, we caught 35% fewer sablefish in the illuminated trawl compared to that of the non-illuminated trawl. This may or may not be a bad finding, as you know, sablefish can be a constrained species in the West Coast groundfish bottom trawl fishery. They are largely targeted in the DTS fishery over the slope break and the continental shelf break, and that's the Dover sole, thorny heads, and sablefish fishery. But over on the inner shelf, you know, a lot of fishermen may not want to catch their sablefish there. They maybe want to save it for the other fishery. So if they are being constrained by sablefish, losing that catch may or may not be necessarily a bad thing for them, but it's ultimately going to depend on sort of their quota mixture and what they have and if it will work for them or not. But nonetheless, we did see a catch loss of sablefish. Looking at our other target species, Dover sole, petrale, and lingcod, overall there's a general trend of catching fewer fish overall in the illuminated trawl. However, once we incorporate our confidence intervals into that mean value, we see no significant effect between the two trawls. And then looking at the physiological condition between the two trawls, Fulton's condition factor, there's no difference between the two trawls that we found. The somatic fat content did not differ between the two trawls. Looking at the stress hormones, lactate, glucose, and cortisol. For lactate and glucose, we did not see effect between the two trawls. However, for cortisol here, we did see a significant difference. And what we found was the illuminated, for Pacific halibut caught in the illuminated trawl, their levels of cortisol were significantly higher than Pacific halibut caught in the non-illuminated trawl. So that was a very interesting finding that we found, and we're hoping to be able to conduct further research to kind of further look into this or collect further data to see how it may move forward. So that was an interesting finding. These are just the mean light levels that were collected per paired for analysis. The open circles is the illuminated trawl, closed circles are the non-illuminated trawl. And really what we see here is you just got about a magnitude of order of difference of light between the illuminated trawl and the non-illuminated trawl. So I just want to show that. And so the conclusion of this particular study, we demonstrated the ability to significantly reduce Pacific halibut bycatch using illumination. This halibut is likely to continue to constrain some fishers from fully utilizing their quota shares of healthier groundfish stocks in the West Coast. The results from our study, they provide a simple gear modification to seek to reduce Pacific halibut bycatch. So that was a nice result. And also we were able to reduce the bycatch of halibut before trawl capture. So this has the benefits of potentially reducing unobserved and unaccounted mortality that can occur in that capture escape processes that can occur within the trawl. So getting them out before entering the trawl is always a benefit. And then lastly, although these are all positive results above in our findings, I just want to stress that it's important to note that fishers would need to consider economic trade-offs between bycatch reduction and increased fishing effort needed to offset any reduction in catch caused by the artificial illumination. And the quota fisheries that we have, everybody's quota mixture is a little bit different. And so the trade-offs between bycatch reduction and catch loss is going to differ between platform and fisher's business plan, but it's something to consider with these types of selective devices. And this work can be found in the Journal of Fisheries Research. You can locate it there for the full scope of the work, or again, contact us and we'll get a copy to you. Okay, so that kind of wraps up the trawl component of this presentation, and now I'll just focus on some proposed research that we have right now submitted to a funding source. And this research would occur in the Pacific halibut longline fishery. And this would be testing modified circle hooks to reduce yelloweye rockfish bycatch in the Pacific halibut longline fishery with a specific focus on Area 2A. It's a collaborative project between the Pacific States Marine Fisheries Commission, OSU Simmers, IPHC, and NIMS Northwest Fisheries Science Center, and Halibut Fishers. So background to this work, in the West Coast and Alaska fisheries, the retention of yelloweye rockfish is prohibited, and conservation zones along the West Coast have been established to protect the stock. So currently, yelloweye rockfish is in the rebuilding phase from being overfished. As of now, the current projection is that they'll be fully rebuilt in 2029. In IPHC Regulatory Area 2A, this is the Washington, Oregon, Northern California. In 2019, the halibut catch limit was 115 metric tons, and that resulted in about 7.4 metric tons of yelloweye rockfish, which was up much higher than previous years. For all commercial fisheries along the West Coast in that year, the yelloweye rockfish ACL was approximately 47 metric tons. So that bycatch in 2019 represented approximately 15% of the yelloweye ACL for the West Coast. So that's something to kind of keep an eye on. Hopefully, it's not something that continues to occur, it's not a trend. But anyhow, nonetheless. As I mentioned, the rebuilding plan for the yelloweye rockfish is for the stock to be fully rebuilt in 2029. So with that, they're likely to continue to be an issue in the directed halibut fishery and other fisheries where their bycatch occurs, for example, trawl fisheries. So a simple method that can reduce bycatch in longline fisheries where the target species is larger than the bycatch species is adding a wire appendage that extends from the hook shank. What this does is it increases the dimension of the hook without altering its specified length, width, bite, or gape. And some examples of this being applied is a Costa Rican pelagic fishery where they're targeting large pelagics and trying to reduce bycatch of sea turtles. So they demonstrated the efficacy to reduce sea turtle catches using these hooks with appendage. Similarly, in the New Zealand snapper fishery, hooks with appendage were reduced to alter the selectivity of snappers. So they used them to reduce the catches of smaller sized snapper compared to larger sized snapper. And there were some successful in doing that. So there's some examples of this potentially being effective. In the Pacific halibut fishery, the difference between yelloweye rockfish and Pacific halibut fishery and their sizes, they get about a mean size of 52 centimeters for yelloweye rockfish, and about 94 centimeters for Pacific halibut. And this is off area 2A. And so this difference in size and differences in mouth orientation and morphology between halibut and yelloweye rockfish suggests that modified hooks with an appendage or a hook size could potentially reduce that bycatch. The methods here is that we would conduct a catch comparison analysis to determine if we change from an unmodified to a modified circle hook, as well as the hook size, if it could affect the catch rates and size of halibut and yelloweye rockfish. The must-add circle hooks the model indicated there would use, I would be looking at the 16 and 18-aught hook size. The 18-aught hook size has not been evaluated, its selectivity in the Pacific halibut longline fishery. And so it'd be nice to be able to look at the selectivity of that particular hook size. However, there is some research that does suggest that a larger hook size can have a selectivity effect on halibut and rockfishes. The appendages that would be tested would consist of stainless steel, approximately 3 millimeters in diameter, and it would be brazed onto the hook on the hook shank near the eye, and it would extend approximately 7.5 centimeters in length at one of two angles, 45 or 90 degrees angles, and this would be relative to the plane of the native curve and the point of the hook. And here's an example of those appendages placed on the hooks. The bottom row is 16-aught hooks, 18-aught hooks on the top. Your far left is an appendage at a 90-degree angle. Center is a 45-degree angle. And in the right, that's our control. We're just looking at just hook size between a 16 and an 18-aught hook. So the methods, to determine if there's a temporal component in the catch of halibut and or yelloweye rockfish, hook timers will be placed on the ganyons. Comparison of time to capture between halibut and rockfishes would allow for an evaluation of a potential behavioral difference in the capture of these species. So as an animal interacts with the hook on the ganyon, it would trigger the release mechanism on the hook timer, and it would start taking time, and we would be able to look back into the logbook where the time the gear is deployed to determine how long it sat there before it was attacked. Data on hooking location would also be collected, and this is to better understand how halibut and rockfish attack the different hook types and sizes that we're looking to test, and how that may relate to post-release mortality. And then periodically video camera systems would be used along the ground line to look at how halibut and rockfishes interact with these different hook designs and hook sizes, just to gather some more information on their behavior. Anticipated results, potential impacts of this work. We would provide data on the selectivity of 16 and 18-aught hooks with and without an appendage. As I mentioned, that 18-aught hook has not been examined in the fishery. If modified hooks and or a larger hook size can reduce yelloweye rockfish bycatch, this will reduce the mortality and improve fishers' catch efficiency of Pacific halibut. And further, the benefit of using hook timers provides great potential to expand our understanding of species-specific contributions to gear saturation. And this data may have potentially helped to improve the standardization of the catch rates in IPHC's Fishery Independent Survey and strengthening the coastwide management of the resource. So those are just some kind of anticipated results and just some potential impacts of this proposed work. With that, just moving to acknowledgements, I think our funding sources for the projects we presented the data on is the NOAA's Bycatch Reduction Engineering Program, the Northwest Fisheries Science Center for facility use and collaborative project support. Our co-authors, our collaborators, our at-sea volunteers and assistants, can't do it without them. And then all the people that had all these great photos I was able to find on the internet that weren't mine to be able to put into this presentation. So I'd like to thank them for that. And then, last but not least, thank IPHC for having me today to present this work and allow us to kind of showcase the work we've been doing along the West Coast with species selectivity, in particular Pacific halibut. And then the seminar series organizers for putting this all together. And then those of you who all tuned in to listen to our work, hope you found it interesting and enjoyed it. And I guess with that, I'll turn it over and free for questions.
Thanks. Yeah, we have We have two questions right now online here. We have from William Jasper. He asks, were the effects of the trawl exclusion gear on excluded fish examined, specifically thinking of damage or mortality rates?
In those specific two studies, we did not. We have an earlier study, it was done in, I think, 2015, where we did do mortality estimates on Pacific halibut caught in the trawl and in the recapture bag, following the West Coast Groundfish Observer Program's protocol for determining whether halibut was in poor, excellent, or good condition, and also the IPHC's protocol they have as well. And on the halibut that we caught between the two trawls, we did not see an effect of the excluder increasing our mortality estimates of those fish caught in the recapture bag. So the sorting grid that we looked at, it didn't appear to have an effect, at least on our estimates that we provided for those halibut.
Okay, thank you. Next question is from Maggie Summer, and she asks, do you have any experience yet using the circle hooks with appendage? And if so, does it complicate gear handling in terms of baiting, deployment, and retrieval? And she also says, thank you.
Oh, you're welcome. Yeah, no, very good question. I myself do not have any experience with it. We've worked with those, or not say worked, but found the appendage of the circle hooks in those other two studies, and then there was a third study conducted on the East Coast that looked at appendages. About the gear feasibility, this gear would apply to snap gear, people that are using that kind of configuration. And in Area 2A, it's our understanding that there's a relatively large amount of fishers that do fish the long line configuration with snap gear, but it would not work if it was not snap gear. So it's very specific to that gear. So very good question.
And we have one more question right now, which I'll read in a second. Just a reminder to the rest of the audience, if you do have questions for Dr. Lomeli, please enter them in the questions tab. So this question is from Ian Stewart, and he says, great talk, Mark. It is clear that different tools will potentially be useful for different target fisheries. Could you speak to the cost of these various trawl gear modifications relative to standard gear, and whether you know of anyone trying them in a production fishing operation?
Yeah, the gear, it varies, from a couple $1,000s upwards to, $15,000, $20,000, depending on materials used, the size of the gear, whatnot. The gear we looked at and are presented for the excluders, those are approximately $8,000 to $12,000 excluder devices. There's some fishers that are using sorting grid devices along our coast. It really varies from vessel to vessel and giving what their fishing scheme is and their quota mix. So other people may have a more bycatch constraints than somebody else, and so it really varies across platform and across the business plan, and also the markets. But there are the devices are periodically used. I wouldn't say they're being used, like coast wide or all your vessels using them, but it's data that's out there, and it's presentable for fishers need it or need a solution to help something. We've provided sort of that information to kind of help them with their catch their quota systems and minimize bycatch.
Thank you. That's all we have online at the moment, Claude.
Okay. Excuse me. Thank you, Mark. I had one question here before we wrap it up, and I don't recall on the light study that you did. Did you look at the catch rates on other similar kind of sized flatfish? So maybe arrowtooth flounder. Did they have a similar behavior response to the light? And if not, do you have any hypotheses on why halibut are reacting one way to the light and the other flatfish are not?
Mm-hmm. Yeah, we didn't encounter very many arrowtooth flounder in that work. usually you can't get away from those things, but during that time there wasn't very much ATF around. I think halibut are such, they differ and just in their swimming abilities as opposed to say a Dover sole or a petrale sole. There's been some previous work done. Craig Rose did some work looking at the behavior of halibut in front of trawls, and show that those halibut can really swim in front of that trawl for a really long time before either falling back in or moving to somewhere else in the area. And so I think it's their ability to perceive the trawl gear in the presence of illumination and having that swimming ability to either stay in front of that trawl and not fatigue or exhaust and drift back into the cod end, or to be able to rise up. Their behavior may ultimately have them rise up above. There's been some Ditson imagery that Waldo Wakefield and some others have collected when they're looking at this selective flatfish trawl and how species responded to it. This was in the absence of illumination, but using the Ditson imaging sonar, they showed a halibut sort of maintaining in front of the wings and sweeps, or not sweeps, the lower bridle. Then ultimately the halibut just kind of kick up and he just rose up over those wings and avoided the trawl capture. And so, and in our work, I think weren't able to illustrate it yet, but I think we're seeing a similar effect where they're able to maintain their distance in front of this trawl, or identify these trawl components and rise up over them, as opposed to drifting back. And the Dover sole or petrale just may not have much of it, may have potentially a less tendency to want to rise up over like a halibut would. But that needs to be systematically tested to determine that.
Awesome. Well, thanks a lot for your time today, Mark. We really appreciate you sharing your knowledge with us, and thanks to all the audience members who attended as well. And as mentioned before, recorded version of this talk will show up on our website sometime later in the week, likely. And please stay tuned for further installments of IPHC seminars in the future. Thanks, everybody.
Okay, thank you. Bye.